Bismillahirrahmanirrahim. We are now going through our 10th recorded lecture. We finished shear force and bending moment diagram in the previous lecture. However, the problem 5.51 that we solved in the end was not given in the solution manual in a very nice manner. So I'm just going through that problem once again. I will be briefly going over this problem. So let us look at this problem 551 first. This was the problem. We had distributed load over the complete length L of the beam, and the distributed load was not uniform. It was increasing from zero value to a maximum value which was equal to W naught. This W naught was not given in the statement of the problem. However, this variation of W with X was given to us. So when X is 0, which is the left end, the load is going to be equal to 0 when we substitute X equal to 0 in this. And when we substitute X is equal to L, we get W is equal to W naught. So the height here is going to be equal to W naught. At X equal to L, W is equal to W naught. So when we draw the free body diagram for the beam to determine the external reactions, we have to convert this distributed load to equivalent concentrated load. And that equivalent concentrated load is shown here. It is W naught L by 2. That is going to be equal to the area under the load curve, which is a triangle. So half into base is length L, and height is W naught. So half into L into W naught. So W naught L by 2 is the equivalent concentrated load. And this load is going to be acting at the centroid of the region. We have a triangle, so centroid of the triangle is 1/3 of the length from the right angle. Right angle is here at end B. So it is going to be acting at 1/3 of the length L by 3 from this end B. So we have this free body diagram, so we can now find this is the total load, equivalent load, half into L into W naught. Now we take moment about point B to find the value of RA, so we get this value of RA. RA multiplied by L, we are taking clockwise positive, minus W naught L by 2 into perpendicular distance from point B is L by 3. So W naught L by 2 into L by 3. This gives us RA is equal to W naught L by 6. And when we sum the forces in vertical directions, we get RP is equal to W naught L by 3. Now we consider a section. Only one section is required to be considered because we just have one distributed load. So we will be considering only one section. So we take a section at a distance X from the left end. The range for this section is going to be from 0 to L. Whatever functions we get for shear force and bending moment, those functions are going to be valid from X is equal to 0 to X is equal to L, which is the length over which we have the distributed load. Now, when we consider this section at a distance X from the left end, we have a shear force V and a bending moment M acting on this section, and RA we have already found. It is W naught L by 6. We found it here. Now we have to convert this equivalent load, this distributed load which is acting on this section. We are considering the left hand section. So on this left hand section, whatever is the distributed load, that is to be converted to equivalent concentrated load. Remember, it is not going to be same as the total concentrated load, which was W naught L by 2, because this equivalent load was for the complete distributed load acting over length L. But now we are considering length X of the beam only. So it is going to be half into base is going to be X, and this height is going to be W naught x over L as given to us in the statement of the problem. W is equal to W naught x over L. So half into x into W naught x over L, which is going to be W naught over 2 x squared by L. So we can sum the forces in y directions. That gives us V is equal to this, V plus this W naught by 2 x square over L, and plus W naught L over 6 is going to be equal to 0, minus W minus this, and plus RA, which is W naught L by 6, is equal to 0. So we get V is equal to this. And when we take moment about the section, we have M is equal to this, moment produced by RA W naught L by 6 into X, and moment produced by, now this load W naught half W naught x squared by L, this is going to be acting at 1/3 of this length X. So distance of this equivalent concentrated load from the section is going to be x by 3. So half into W naught x squared by L, which is the equivalent concentrated load, multiplied by x by 3, which is the perpendicular distance from the section. So M comes out to be equal to this. Now for M max, dm by dx which is equal to V. We have studied that in the load, shear and moment relationships. We know that V is equal to dm by dx. So for maximum bending moment, we must have slope equal to 0 at that point. So we must put dm by dx is equal to 0, and since dm by dx is equal to V, so we just put V equal to 0 and find the value of x. That gives us, we just substitute this right hand side equal to, just put this right hand side equal to 0. That gives you x is equal to L over under root 3. So that is the location where you are going to have the maximum bending moment, and you can then find the maximum bending moment by substituting this value of x into the expression for bending moment, which we have already found here from the section. So we can substitute this value of x where we have the maximum bending moment, and that gives us the value of maximum bending moment. This is what we were required to find in the problem. The problem statement was that determine the equations of the shear and bending moment curves for the beam. So we have found the this is the shear force expression, and this is the bending moment expression. These are the two equations for shear and bending moment for the beam. And we also had to find the maximum absolute value of the bending moment, which is this. However, I also wanted to talk about the drawing of shear force and bending moment diagram using the load, shear and moment relationships. Now, drawing the shear force diagram. Shear force diagram is going to be equal to this. We know that V is equal to V2 minus V1 is equal to negative of area under load curve. Now, and we also know that W dV by dx is equal to minus W. dV by dx is equal to minus W. So the slope of the shear force curve is going to be equal to minus W. Now at the left end, the value of W is 0. The value of W here at point A, it is 0. So that means slope of the shear force curve at this point is going to be equal to 0. So the curve is going to start from the any externally applied force or the reaction, whatever we have at this end, we have RA, so it is going to start from the value of RA. And at this point A, the slope of shear force curve should be equal to 0. So it will start with 0 slope. And then, since dV by dx is equal to minus W, so that means it will continue to become more and more negative. The slope will continue to become more and more negative. dV by dx, as W is increasing from x equal to 0 to x equal to L, the value of W is increasing. So that means since dV by dx is equal to minus W, so that means the slope of the shear force curve will keep becoming more and more negative. So the curve is going to be like this, and we have already located the point where we have shear force equal to 0, so it will pass the V equal to 0 point at this position where x is equal to L over under root 3. So the curve is going to be like this. Then we go to the bending moment, and as we know that at the two extremes, at points A and B, the value of bending moment would be equal to 0 because there is no externally applied couple at these two ends. So the value of bending moment is going to be 0 at this point, it is going to be 0 at this point, at A and B. Then if you look at the shear force diagram, in this region we have the positive area. So the area is above V equal to 0 line, so we take this area as positive. So delta M for this region is going to be positive. That means M is going to increase. So from this point up to this point, M is going to increase. And after this, the shear force has become negative. It is below the V equal to 0 line. So this area will be taken as negative. So the delta M is going to be negative. So the value of bending moment will start to decrease from here. Again, we know that M is equal to dm by dx is equal to V. The slope of the bending moment curve is equal to the value of the shear force. In this region, the value of shear force is positive. It is maximum here, maximum positive here, then it is decreasing and it becomes 0 here. So it will start from 0 value. It will start with the positive slope, which will keep decreasing, and at this point the slope will become equal to 0, and then after this it will start to decrease because now we have negative area for the shear force curve. So it will end up at 0. Now look at the slope. Slope is 0 over here, so it is starting from 0 slope and it is becoming more and more negative. So the slope keeps becoming more and more negative. So that is how we can just plot the shear force and bending moment diagrams without making any calculations for the values. In fact, the values are not given to us here, but we can still draw the shear force and bending moment diagram using the load, moment and shear relationships. Now we come to we have completed our discussion on this shear force and bending moment diagram, and now we talk about one more topic on beam, which is going to be the shear force in beams. So this is given in chapter 6. So we are now starting chapter 6 of the book. Now we have already studied that the shear force is actually the resultant of all shear stresses which are acting on a cross section. Shear stress is going to be in plane stress, so it can be in this direction, it can be in this direction. This is the cross section. This is the cross section of the beam. the beam length is this. The beam length is increasing in this direction. So, and this is the cross section. So shear force can be in this direction, shear force can be in this direction. Now we know that the shear force which is in transverse direction, that is the resultant of all shear stresses which are acting on the cross section. And since shear force is in y direction, so that means when we use the equation in y direction, we have in y direction the shear force perpendicular to this plane is x-axis, perpendicular to this cross section, which is going to be along the beam length, that is the x direction, y direction is vertical, and z direction is horizontal on the cross section. So the shear stress which is going to be acting in y direction, the outward normal is x, and the direction of shear stress is going to be along y, so it is going to be tau xy. This is going to be tau xy. The first subscript indicates the outward direction of outward normal, and the second subscript indicates the direction of shear stress. So this shear stress along y direction is going to be tau xy, and shear stress can also be in this direction, in this plane. It can be in the vertical direction on the cross section, it can be in the horizontal direction on the cross section. So the horizontal one is going to be tau xz. Outward normal is still in the x direction, so first subscript is x, and second subscripts indicating the direction of shear stress, that is in z direction, so it is tau xz. Now when we apply the equation in chapter 5, we have been talking about the maximum compressive or tensile stresses, because that is very important for the design of beam. However, the shear stress can also be important in certain situations, so we must know about the maximum shear stress in beam. Now if we apply the equation, if we consider the y components, then the resultant of all shear stresses which are acting on the cross section, tau xy is just the one which is acting on this differential area. So tau xy dA is the shear force which is acting on this differential area. And this is since this is in y direction, so the resultant will be equal to the net force which is applied on the cross section in the y direction, which is minus v. So in when we consider the y components, the resultant of all shear stresses is equal to minus v. And since there is no force applied in the z direction, there is no force acting on the cross section in z direction, so when we consider the z components, then tau xz dA, integral of tau xz dA is going to be equal to 0. This tau xz dA is going to be equal to 0. Integral of this will be equal to 0 because we don't have a force which is applied on the cross section in z direction. We only have shear force which is in transverse direction, y direction. Now tau xz is equal to 0. However, we can have shear stress in this direction on a plane which is, say, a horizontal plane in this direction. If we consider this shear force along x, so perpendicular to this, the plane is actually a horizontal plane, so this is going to be xz plane. If you look at this figure again, We are now talking of XZ plane. That is also going to be a horizontal plane. So in the horizontal plane, this XZ plane, the perpendicular to this is y-axis. Perpendicular to this is y-axis. So we are going to have a shear stress on this horizontal plane, and this shear stress is going to be there because we have studied in chapter 1 that the shear stress on two orthogonal planes which are at 90 degree to each other is going to be equal. That we have already discussed in chapter 1. So whatever shear stress we have on the vertical plane, which is this tau xy, this must be balanced by a shear stress which is going to be tau yx on the horizontal plane. So these two, we have already studied the equality of these two. They must produce couples in opposite directions so that net couple becomes 0. So that means we must there is going to be some horizontal shear also, which is going to be in the x direction in horizontal plane. Now we move on to the shear force is going to be denoted by delta H. Delta H is used for shear force in the book, so delta H is going to be there, and the shear per unit length is denoted by small q, and it is known as shear flow. We are not going to talk about shear flow, but we will be you should know that shear per unit length is the shear flow. We will briefly talk about it when we derive the equation for shear stress. Before that, we will just talk about shear per unit length q, which is known as shear flow. Now we consider a beam segment of length delta x. We consider, say we have this beam, this is the length of the beam, and this is the cross section. Cross section is going to be the YZ plane, y-axis is vertical, this horizontal axis is z, about which bending is going to take place. Now we consider a segment of this beam of length delta x. We consider this small segment of the beam, and we want to know what is going to be the horizontal shear stress acting at this section C prime D prime, at this horizontal fiber. What is going to be the shear stress acting on this? Now say we have already located the neutral axis, and neutral axis is located here. This is the location of the neutral axis. This is the length of the beam, and this is the cross section. This is the length, and this is the cross section. So this axis is going to be z, or the neutral axis, and this is vertical axis on the cross section is going to be y axis, and along the length of the beam we have x axis. So this C prime D prime is located at a distance y1 from the neutral axis. Now when we use the equation summation fx equal to 0, let us look at this figure also, figure 6, this figure. Now when we sum the forces in x direction, we are going to have the existence of this horizontal shear can also be discussed using the concept of bending moment, as we have seen that in the bending moment diagram that we have been plotting in chapter 5, we have seen that bending moment is not going to, in general, it is not going to remain constant over a region. So as we move along the length of the beam, the value of bending moment is going to be different. So it will keep changing. The value of bending moment will keep changing as we move along the length of the beam. And when bending moment changes, that means the normal stress which is acting at that section is going to be different from normal stress at another section. So if we consider this beam segment, then on this CC prime, on this section, bending moment is going to be different than the bending moment at this section, which is going to be D prime. So there is going to be a difference. That means at the identical location, say at this location C prime D prime, which is at the same distance, the C prime is also at a distance y1 from the neutral axis, and D prime is also at the same distance y1 from the neutral axis. However, the value of stress is going to be different. Value of stress is going to be different. Why? Because the stress, the elastic flexor formula that we have studied in chapter 4, that states that sigma is equal to my over I. My over I. So my over I is the normal stress acting at that section. So when m is different, then the normal stress is also going to be different. And since the area is going to be over which the normal stress is going to be acting is going to be same for on both the sides, we are just considering this beam segment, so we are considering the same area on the left side and on the right side of this segment. So area is going to be same, so that means force is going to be different, because stress, normal stress has different value on this section CC prime than the value of normal stress at section DD prime. So since normal stress is going to be different on the two ends of this beam segment, that means the normal force is going to be different. So that means there is going to be some net force which is going to be acting in horizontal direction at on this beam segment, and this is going to give us the horizontal shear. So when we sum the forces in horizontal directions, here we have this horizontal shear force delta H, which is not known to us yet. We are going to derive a formula for this, and the resultant of this sigma c, this is going to be in positive x direction. So why we are taking compressive stresses? Because we are assuming that we have positive bending, and for positive bending all the fibers above the neutral axis are going to be under compression. So on these segments, this beam segment C prime D, this is above the neutral axis, so it is going to be subjected to compressive stresses on the section CC prime and DD prime. Now the resultant of this sigma c dA is going to be at differential area, and when we consider this total area, it is going to be integral over this area into sigma c dA. That is going to be on the left side on the section CC prime. Similarly, on the section DD prime, the net force is going to be equal to sigma d dA is going to be the force acting on a differential area, and when we integrate that over the complete this region DD prime extended over the cross section, then actually we have this area on the cross section. On the cross section we have this area. So when we integrate over the complete area, we get this force sigma integral sigma d dA, and since this is going to be in negative x direction, so we are using a negative sign here. So the equation written here, it has combined both the sigma c and sigma d in written. The two integrals have already been combined, and now we have this relationship for the horizontal shear. Now we can substitute sigma equal to my over I. So sigma c is going to be equal to mc into y over I, and sigma d is going to be equal to md into y over I. And since we have moved this integral onto the other side, so it will become negative, so we have multiplied inside with the negative sign. So instead of sigma c minus sigma d, it becomes sigma d minus sigma c. So that is equal to my over I. So m has been written outside and y is here, my divided by I, which is the second moment of area for the cross section. So this becomes md minus mc divided by I integral y dA. Integral y dA is the first moment of area. We know that integral y dA is the first moment of area. Now this md minus mc, this is the change in bending moment as we go from this section cc prime to dd prime. As we go from this section to this section, this is the change in bending moment, md minus mc. So that is going to be, we can write that this as delta m, and delta m can be written as dm by dx into the length of this beam segment, which is delta x. Length of this beam segment is delta x. So we can write this is actually delta m, change in bending moment as we go from section cc prime to dd prime. So this is equal to delta m, and delta m can be written as dm by dx into delta x. And we know that dm by dx is equal to shear force V. V is equal to dm by dx from the load, shear and moment relationships that we have studied in chapter 5. We know that V is equal to dm by dx. So we substitute dm by dx equal to V. So instead of md minus mc, we substitute V into delta x. So in this formula, here we substitute V into delta x. And this integral y dA, we are denoting this with capital Q. This is the capital Q. So delta H therefore becomes equal to VQ over I into delta X. V into delta X is M. V into delta X, this is delta M. V into delta X. Delta M is equal to V into delta X. I remains as it is, and this integral has been denoted by capital Q. So we have V delta X Q over I. So it is just rearranged like this, VQ over I into delta X. If we consider the bottom portion from C prime D prime to C double prime D double prime, if we consider the portion below this line C prime D prime, we will still get to the same result. Result is going to be exactly same. So it doesn't matter which side we consider, the top side or the bottom side. The horizontal shear will come out to be same. Now we can find, since we have this relationship for horizontal shear in terms of the length of the beam segment. Delta X is the length of the beam segment. So we can divide this with delta X. So that is going to give us horizontal shear per unit length, delta H divided by delta X, which we defined as shear flow. So that is going to give us small q. This gives us the horizontal shear per unit length. So we just divide the equation by delta X. So small q is equal to VQ over I. Now that is not the final formula that we are going to use. Now the average shear stress, which is going to be acting over the area, we don't find the shear stress at any particular point on this surface. We find the average shear stress on this. So average shear stress is going to be equal to delta H divided by delta A, the average shear force that is going to be acting on this plane, on this area. This is the length of the beam segment. This is the cross section. This should be C1 prime, and this is C1 double prime. Okay, this is D1 double prime. Okay, D1 prime, D prime, D2 prime. D. This should be this should be C1 prime. This should be this is not correctly written. This should be C1 prime, C1 double prime, D1 prime, D1 double prime, D2 prime, D2 double prime. So this should be C2 prime. This should be C1 prime, and this should be C2 prime. So there is some misprinting in the book. Now the horizontal shear is going to be acting on this area. We are considering the bottom side. We are considering, let me again show it to you. We are considering this bottom side. So horizontal shear, we are talking of horizontal shear on this horizontal plane, which is going to be along C prime, D prime. So on the cross section, we have this line. On the length of the beam, we have this line. So this length, this line is going to be, the cross section is going to be like this on this beam. Cross section is going to be like this. So that is shown here. This is the area over which horizontal shear is going to be acting. So the shear stress, average shear stress, is going to be equal to delta H divided by delta A. And this delta X, this is the length of the beam segment that we were considering, delta X. So this side is delta X, and this is the thickness of the beam at this location. Thickness of the beam at this location. Just look at this cross section again. We are talking of this location, this fiber, which is at a distance y1 from the neutral axis. So the thickness of the beam at this location, this length, this is the thickness of the beam at this location. Thickness is going to be along Z. Along Y is known as the depth of the beam. So we divide delta H by delta A, and delta H was equal to VQ over I into delta X, and delta A is equal to this delta X multiplied by thickness of the beam, which is T. So T into delta X is going to be the area over which this horizontal shear is going to be acting. And so when we divide this with delta A, this delta X cancels, and we have VQ over IT. VQ over IT. So this is the average shear stress which is going to be acting on the beam, VQ over IT. So we are going to use this formula, and when we use this formula, V is just going to be the value of shear force at that section, whatever section we are considering. I is going to be the second moment of area of the beam. T is going to be the thickness of the beam at the location where we are finding the average horizontal shear. And Q is integral YdA, so this is going to be just the first moment of area. So we can just calculate a summation ai yi prime. We can make a table, we can divide the region into a number of regular shapes, and we can find the value of I about its own axis, and then use the parallel axis theorem to find the value of I. Value of Q. So the area is to be multiplied with the value of y, summation ai yi, that is going to give us the value of Q, that is the first moment of area. So we can find the value of first moment of area a1 y1 prime for one area, and then if we have two different shapes, then we can find a2 y2 and then add the two, that is going to give us the value of Q. That will become more clear when we solve a problem in the next class. We will stop here. We have taken a little more time because I just wanted to go through problem 5.51 again, so that the load moment and shear relationship could be explained to you, and also how we have written the expressions for shear force and bending moment for the section was also not very clear in the solution that I earlier presented to you. So I hope it is now understood to you, all of you. So we are going to solve a problem on this horizontal shear in the next class, which will further tell you how to calculate the different parameters in this equation. Delta H is equal to shear stress, average shear stress is equal to VQ over IT. Thank you.